Here I am. It is 11 o'clock UTC, so welcome everybody to this 2-hour Transform 2021 tutorial. First of all, I would like to thank Studio X for sponsoring this event. It makes a big difference to have a sponsor. Thank you, Studio X. This year, it's the third round. It's the third Transform, and it's in its current form. It's actually the second. And what you're going to see in the next 2 hours is an absolutely first for Transform. You're going to see a MATLAB / Octave tutorial, which I am very excited about it because Software Underground has a very heavy focus or dominance of Python users. But even though we have a lot of Python users, it's absolutely and by no means the only language that we talk about. There are R users, there are Julia users, there are MATLAB users, and I'm pretty sure many of us Python users originally come from MATLAB. So today we're going to have a tutorial about MRST. The MATLAB Reservoir Simulation Toolbox is a research tool for rapid prototyping and demonstration of new simulation methods and modeling concepts, offering a wide range of data structures and computational methods which you can easily combine to make your own custom-made modeling and simulation tools. The speaker of today is Øystein. He's a research scientist in the computational geoscience group at SINTEF. And he earned his MSc and his PhD in applied mathematics at the Norwegian University of Science and Technology. His focus is numerical methods for flow in porous media with an emphasis on efficient linear and nonlinear solvers. So I'm very pleased and excited to welcome Øystein to the floor.
Thank you very much for that introduction. And again, welcome everyone to this tutorial on reservoir simulation and modeling with the MATLAB Reservoir Simulation Toolbox, or MRST for short. So just like to emphasize this, even though I'm giving this presentation, this toolbox is really a group effort. It's developed by the Computational Geosciences group at SINTEF Digital, and we're based in Oslo, Norway. I would also encourage you all to follow the Slack channel. You can ask questions there, and you'll also find a zip file with all the scripts that we're going to use today and also the slides. The Slack channel is called T21-2-MRST. So first, a quick overview of the tutorial. First, we'll give a short overview of MRST. What's the purpose of this software? How is the software organized? And where can you go to find help? Then we'll look a little bit at how to get started, how to download or clone MRST, how you use and navigate the modules, which is sort of the building blocks of the toolbox. And then we'll go on and solve an incompressible flow problem, a simple gravity-driven flow problem. I think we'll put in a short break at that time, and afterwards we're going to continue looking at the numerical framework. That's sort of the backbone of the toolbox with discrete operators and automatic differentiation and how that works. Look at a quick example on how we can solve the Poisson equation using those building blocks. And then finally, I'm going to spend hopefully quite some time on a more complex example where we'll go through the entire process of creating and simulating a sector model. So first, a short overview of MRST. So what is this toolbox? It's a unique prototyping platform, and it's really geared towards this rapid prototyping. It has standard data formats, data structures and library routines. We have a fully unstructured grid format, and a few sort of enabling technologies for rapid prototyping, which we'll go a little bit through in detail later. Discrete operators, automatic differentiation, and a convenient object-oriented framework. We also go to quite great lengths to support industry standard simulation, which is very handy both for us and for many people who use this toolbox. If you have a model in an industry standard format, you can potentially import that in MRST and simulate on it and use that. Little bit about the user base of the toolbox. You can see on the right-hand side here, this is Google Analytics pattern from our webpage, mrst.no. So you see that we have downloads from all over the world, rather large international user base, and the software has been used in a total of 125 master theses and 62 PhD theses, upwards of 270 journal papers authored by people from outside our group, and approximately 150 proceedings papers. So all in all, it's used both by academia and industry for reservoir simulation to a quite large extent. A little bit on how the software is organized and how it's built. We have a small core with mature and well-tested functionality, which is used in many programs or modules. So you sort of have the core, and then there's a bunch of semi-independent modules that extends on the core functionality with in-source documentation, just as you would find in MATLAB functions. And there's a requirement that all of these modules must have code, examples, and/or tutorials. And this sort of design really simplifies how we distinguish public and in-house to, say, client-specific functionality. And this core module, that sort of holds the basic building blocks of MRST. Includes the grid structure, grid factory routines, petrophysical data, basic fluid models, automatic differentiation library, functionality for setting boundaries, wells and sources, and so on. We have reservoir state, visualization, and so on. So I'm just following the chat here, and I just got the question if we could elaborate about the main difference between MRST, what you're going to see now, and something called OPM, which is the open porous media. And I said the main difference is that OPM is very much more geared towards eclipse type simulations, for those familiar with that. And it really is geared towards and meant to provide much of the same simulator functionality that Eclipse offers. I think my good colleague Olav Møyner is also answering that in the chat, so please follow the chat for a more probably elaborate answer. So please ask questions in the chat in Slack, and we'll try as best as we can to answer the questions as they come. So with the current release, I'd say the software has grown quite large over the years. It's now a total of 57 modules, if I'm not mistaken, and it really ranges over and spans a large variety of applications. So you have everything from, say, grid generation and coarsening, upscaling and multiscale solvers. You have black oil simulation functionality. There's functionality for geomechanics, geochemistry, and geothermal. A pretty extensive CO2 storage laboratory. So there's really a lot of different things you can use here, and pick different parts from the toolbox, and hopefully you can be able to do what you would like yourself. Few words on resources and how to get help on the software. The first and most natural place to start is to go to our website. So that's mrst.no. And here you'll find a bunch of useful links. We'll look a little bit at that webpage later. So you have frequently asked questions, for instance. There's a gallery, and there's, of course, information on how to download the software, and you have a bunch of documentation. There's also a link on that webpage to our user forum, where you can ask questions, and we'll also look a little bit about on that later. And then there's a textbook on MRST, which was published in 2019 by Knut Andreas Lie, an introduction to reservoir simulation using MATLAB and GNU Octave. And this is published as open access, so it's free to download on Cambridge University Press. We actually just got a question about this, I think, yesterday in the channel about the download, and for some reason the download link is currently down, but we're hopefully that's going to be fixed quite soon. In the meantime, you can at least download individual chapters of this book. And this is also a very good book on reservoir simulation in general, both from the numerical side and also from, say, reservoir engineering point of view. In addition, each of the functions in MRST has in-source documentation, so you can just write help, and then the function name And then we get an extensive description of the function, its syntax, and what it does. And then there's quite a large collection of tutorial codes and examples that you can use and learn about how to use the software. And then there's also these online tutorials recorded, just like this one, which are recorded from before, where you can go and look and see if and use those to learn how to use the software. And then I would just like to mention that there's a new book. It's in press, and I think it's scheduled to be published in September this year on Cambridge University Press. Also going to be open access, and this is on advanced modeling with MRST. And there's going to be quite a lot of interesting work here. You'll have something on unstructured constrained Voronoi grids. There's nonlinear finite volume methods, for instance, a large chapter on multiscale methods. And there's going to be work on fractures, geothermal systems, and so on. Okay, so I think that's enough on how to get help on the software. Next thing, a few words on the requirements that you need, software requirements in order to use MRST. The bare minimum that you need is a MATLAB version 7.4 or R2007A or later. No additional toolboxes needed. There is, however, certain modules and features that would not work in 2007A, and this is some of the automatic differentiation relies on class def things that came in 2008A, and there's also various scripts and examples that use syntax from random numbers from 2007B. Then there's a little bit on use of the tilde operator from 2009 to ignore return values. And some of the solvers, for instance, the fully implicit one, are not very efficient on versions which are older than 2011B. But in general, as I said, you should be able to do most of the things with a MATLAB version 2008B. Also, for those of you using GNU Octave, most of MRST can be used with Octave, and maybe except for some of the GUIs. There was actually a release of this toolbox yesterday, MRST 2021A, in which there are a number of upgrades to how we deal with Octave. So there should be a significantly better performance if you're using the latest release. So if you're using GNU Octave, as I said in the instructions in Slack, I really recommend that you download the latest release or that you work on the developer version of MRST. I'll come to that in how to do that in the next slide. There's a word for those using GNU Octave. I think I would also just mention that there is an Octave module, which is still lying on our web pages. That's not needed in the latest release. If you're on Octave, this should be recognized by MRST, and it should do the necessary adjustments in order for you to run stuff in Octave. Few external dependencies that you may need if you're using some parts of the toolbox. Some iterative linear solvers would require you to have AGMG or AMGCL. These are algebraic multigrid solvers and compiled for higher performance. And then there's a few dependencies for graph partitioning. That's the MATLAB Boost graph library and the METIS for partitioning of fully unstructured grids. Okay, I think that's enough on about MRST, and it's time to get started. So the first thing we'll do is just to go through how to actually get the software. I hope that most of you have already done so already. But what you do is that you go to mrst.no, and there's a link for download, and you can download the latest release version. And this is a free software released under the GNU General Public License, and it's released twice a year. The latest release, as I said, was yesterday, MRST 2021A. So if you download that, this is provided as a self-contained archive, MRST2021A.zip, if you download the latest release. And we recommend that you join the MRST Announce Google group. There you will follow both announcements regarding releases and also other exciting stuff regarding the software. So that's essentially what you do in order to work with a release version of MRST. If you would rather like to follow the development actively, you can of course clone the code from Bitbucket. Then you'll also have to potentially accept the occasional bug and broken feature. We usually try to keep, and we do our best, of course, to keep things running all the time. But if you want to follow the development actively, then you can use the version from Bitbucket. So in order to install MRST, what you do if you have downloaded the zip file is that you simply unzip to a subfolder, say MRST 2021A, if that's the version that you're working on in your current working directory. And once this is extracted, you can just navigate MATLAB to that folder. So on Linux and Mac, that would be like this. And if you're on Windows, that would be something like this, assuming that you've extracted your files to the home directory. The next thing you do is then to run the startup file to activate MRST. And this startup file can, of course, also be called directly in your startup script in MATLAB. And so this is what I usually do in my startup script, the one which is run when you start up MATLAB. I have this in my startup script, which makes sure that MRST 2021A is loaded once you start MATLAB. This is the point where I'll actually switch to do some actual coding in MATLAB. So I'll just show you here what happens if you run the startup script in the MATLAB Reservoir Simulation Toolbox. You'll then be prompted with a message that welcomes you to MRST, and it says which version you're on. So now we're on the release version, which is version 2021A. And there's a bunch of links in this startup message. The first one is mrst.no. So let's just go to that and look at what the web page looks like. Maybe some of you have been here already. Hopefully you've been here and downloaded MRST. So you go to the download, and then you can download the zip file here. You can also find other version, a little bit of terms of usage, key references if you're going to cite the use of the software. And then there's, of course, extensive documentation where you can look at both key publications, if you like, of the software. And you can go to, for instance, journal publications published by people outside the group. A lot of information on the webpage, so I encourage you to go there and check it out. Another thing that you'll see here is that there's a link to the forum. And if you go to that, you can access the MRST user group forum. This is a Google group. And on here, you will find a bunch of previously asked questions. You can search the history and see if you find something that matches what you're looking for. Or if you have a question yourself, you can, of course, ask a question here, and either we will try to answer that, or maybe someone else who uses the software can answer that. And this is also where we are releasing. This is also where we are announcing our releases and so on. So that's a few useful links. In order to use the software, there's a number of ways to start. You see a list of useful commands for getting started here. Very first one is MRST examples. This is going to list a bunch of introductory examples. You can see here that when we issue that command, it says that MRST, the module core, has 14 examples. And then you can click on one of those and read the example. It has quite a lot of extensive comments and documentation. So that's a nice way to get started. And if you would like to look at examples for a specific module, for instance, I would like to see examples for the AD black oil module. I'll do MRST examples AD black oil, and that's going to list all the examples that follows the AD black oil module. You can click on that, and then you can run and see. And this is probably one of the easiest ways of getting started with MRST. find an example that looks like it does somewhat like what you want to do, and then modify the example to your needs. So let's just bring up that message once more. You can call MRST startup message to bring up this message again if you would like these links repeated. So as I mentioned in the introduction, MRST is built on modules. And in order to navigate these modules, there's a number of different tools that you can use. The very first one is MRST path. This you can use to list all the modules that are registered for the software. And if you do that, you'll see a long list. And for instance, you can see here that the AD Blackoil module is registered, and it resides in this folder right here. So that's one way to see all the modules that are in MRST and available. Another way to do this is to use the MRST module command, and that takes in different types of arguments. One way to call that is with a string GUI. If you click on that, you're going to get up a panel just like this. And here you can see all the modules that we just listed in the command window. And if I now, in the command window, do MRST module list, you'll see that we have currently no active MRST modules. But if I would like to add modules, you can just check a couple of modules, say that we would like the AD Blackoil module, and we would like the virtual element method module. And if I now do MRST list, you'll see that we have added the virtual element method module and the AD Blackoil module. You can also unload modules. That means that we're removing them from the list of active modules. If I now do MRST module list, you'll see that we have no active modules. So that's one way of navigating the modules. And let's just bring up the startup message again. Another way, and that's probably the one that you're going to use the most, that's just to say MRST module and then add, and then the name of the module that you would like to add, or modules. So say I want to add the Blackoil module, and that's it. So if I now do MRST module list, you'll see that the currently active MRST module is AD Blackoil. Let's do MRST module clear, and that's going to take away all the modules again that I've loaded. So that's essentially how you can load modules. A very convenient thing with this is, with working with modules, is that if you're working on a project, you can register that as your own module. And the way you do that is, and the way I like to do that, is that in my startup folder, or say that the root folder of MRST, for me, that's this folder right here. So in MRST 2021A, I make a script, which is called startup user. And that's what you can see on the left-hand side here. Just enlarge the editor a little bit. So when the startup file of MRST is called, it's also going to look for a startup user file. And if it has that, it's going to run that. And this is where you can register your own modules if you like. So here you can see that I've used the function MRST path with an argument register. And that verb tells the function that we're going to register or re-register, a module, which we will call. And the first input argument here is the module name. And the second input argument is the path to that module. So this has been run when I ran my startup. And if you look at MRST path list, we can see that Transform 2021 is something that I registered as a module, and it has this location that you see there. Very convenient if you're working on your own project, and I can do MRST module add and Transform 2021. And now anywhere that I am in MATLAB and when I'm working in MRST, I will have access to everything which I put into this folder module. So for instance, now you could take the zip file that is in the MRST channel that I provided a little earlier this morning, and you can put it in a location where you would like to have it and register as a module. So that you can do, for instance, after this tutorial and see how that would work and how you should organize your work when you're doing your own projects in MRST. let's just bring up the startup message once more. And the last thing I thought I'd mention about this startup message is that MRST has a bunch of data sets that you can download, or it supports a bunch of data sets that you can download. And a very convenient tool for navigating those is to use the MRST dataset GUI. So if you just click on that, you'll get this thing up here. And on the left-hand side, there's a long list of different data sets that are available for download in MRST. So for instance, if we click at the Johansen dataset, there's a little bit of information here about what this is. This is a formation candidate site for large-scale CO2 storage offshore the southwest coast of Norway. You can click on download to get that, or you can go to the web page, and you can also click on the button which says examples here, and then that's going to list in the command window the examples that use this dataset in MRST. So that's very convenient, and you can also here, if you like, register your own datasets if you're using that on a regular basis. One thing which I think I forgot to mention is that we also have, regarding the modules, Module Explorer. So let's just click on that, and you'll see here, I'll just enlarge this a little bit, a list of all the modules available on the left-hand side. So for instance, if we look at the AD black oil module, you'll see here in the upper panel in the middle here, a long description about this module, what it does and what it's meant for. And then on the right-hand side, you have a long list of examples. So these are all the 19 examples that are in the AD black oil module. If you click on one of them, you'll also see a description of this example. And then at the bottom here, there's a panel which lists the relevant literature. If you're going to use, say, a module in work, or if you want a more in-depth description of how this module works, you can go to these resources. Or if you're using it in, say, a scientific publication, you could use one of these to cite your work. So I think that's it regarding navigating modules and this startup script. And the next thing we will go through here is actually a very first example. So the first thing we'll look at is an incompressible flow problem. So for that, we're going to use the incomp gravity column script that's also in the zip file that I provided you with earlier this morning. So if you open that, you'll see that the first thing we're doing in this script is to add the modules that we're going to use. And in this case, we're going to use the incomp module, which is for incompressible flow problems. So let's just do MRST module clear, and then MRST module list to see that there's no active modules. And then MRST module add incomp here is the first thing we do. We're adding the incomp module. So let's just do MRST module list to see that we've now added that module. Now, the next thing that we need to do is to put on gravity, because we're now going to simulate a gravity column. So we would like to make sure that we're actually taking gravity into effect when we're simulating. And we do this with the function gravity, which can be used in a number of ways. If I just type gravity in the command window, just gravity, then it's going to say what the gravity currently is. And this is now a vector, and it's positive and equal to the gravitational acceleration that we're used to see in the positive z direction. You can also use it to set the gravity to something else. So if I, for instance, want it to be gravity working at an angle of 45 degrees with the x and y-axis, you say gravity 1, 1. If I now just say gravity, you'll see that this is what the gravity looks like. Since we're working in physical space, since we're on Earth, I'll put it back to what it was, positive in the 9.8066 in the positive z direction. So then we have gravity. Next thing we need is a computational grid. And for this example, we're going to use a simple Cartesian grid. So that's what we're constructing in this line number 6 here. The dimensions of this grid will be a 2 by 2 by 30 cells, and we're going to use physical dimensions. So that's the second argument of 1 by 1 by 30 meters. So let's just make that grid and look at what the grid structure looks like. So you see that the G has a number of fields. It has cells, faces, and nodes, most notably. And if we see G.cells, you can see that this has a num field, which says how many cells we have. And the rest here is essentially just index maps telling us which faces makes up each cell. So in order to actually do any simulations on this, we need geometric information about the grid as well. We need, in particular, the grid cell volumes. We need the centroids of the grid cells. We need areas of all our faces of the grid. We need centroids of the faces, and we need normals of each face. So we're then computing geometry in this line here. And if I now type G.cells, you'll see that the grid.cells has a few more fields. One is volumes, one for each grid cell, and one cell centroids, which holds the centroids for each of the grid cells, and that's the number of grid cells by 3 array, one for each of the spatial dimensions. So let's now just plot the grid and see what it looks like. That's what we're doing here. And this is what we got. Looks good. It has a 2 by 2 by 30 grid cells. And the physical dimensions, as you see on the axis here, is 1 by 1 by 30. Okay, so far so good. The next thing we need is to actually populate this grid with petrophysical properties. And we do that in MRST by the function makeRock. And this function takes in 3 arguments. The first one is the grid structure that we're going to create a rock object for. The second input argument is the permeability, which we in this case set to 0.1 Darcy. And the last argument is 1, which is just the porosity. We'll just simply using 1 here for the porosity. That's not something you would typically see in subsurface applications, but that's what we're using in this example. Another useful thing I think to notice here is that MRST uses SI units by conversion. So that's the standard. And if you would like to give your units, say in Darcy, which is very common for permeability, you just use this Darcy, which is implemented. And you can see that Darcy is just equal to the number of square meters, I believe, which is the unit for Darcy for permeability in SI units. So now we made that rock field, and it says if we do MRST module, rock, and look at what the rock looks like. It has it's a structure with 2 fields, one which is called perm, which has 120 values, one for each cell in the grid, and one which is called poro, so the porosity for one for each cell in the grid. So now we have the computational grid. We populate it with petrophysical properties. Next thing we need is a fluid model, a fluid object. And in this example, we're using the incompressible solvers. So we're then using the init single fluid function to construct a fluid object. And what we're giving into this is, first of all, the viscosity, which we just say is equal to 1 in this case. It doesn't really matter because it's single phase. And then the second argument is the density, which we put to 1,000 kilograms per cubic meter. Let's just go ahead and construct that fluid object. So then we have the fluid object. If we look at that, you can see that it has a density field and a bunch of other functionality. In this incomp framework, we actually have one function for each of the phases that we could have, the water, oil, and gas phases. in this case, we only have the water phase, so those are the only non-empty functions. So now we have the fluid object, and now we would like to put on boundary conditions on our model. So what we would like to do in this case is to apply a constant pressure on the 4 top faces of the model. And you can apply and set boundary conditions in a number of ways in MRST. Maybe the simplest way to do it for Cartesian grids is simply to use the p side function. It has a similar function flux side. P side is for setting pressure boundary conditions, and flux side is for setting flux type boundary conditions. It takes in a potentially empty boundary condition, which is a structure, and then it takes in the grid, and then you give a string which says what side of the model you would like to apply your boundary condition. In this case, we want it on the top, and then we just give the value, which we put to 100 bars in this case. So then we have a boundary condition struct. You can see here that it has a phase field, which is just the phases that are used in the boundary condition. The type of boundary condition that we prescribe to each of these phases, they're all pressure. And then there's a value field. And then finally, there's a saturation field. This is only needed if we do multiphase simulation and we have an injection boundary, but it's always there by convention. So let's just now plot phases. And we want to plot the phases that's in this boundary condition struct, and we just give them a red color. And if you look at the figure now, you will see that the 4 top phases, those are the phases where we have applied our boundary condition. Just one final thing that we need in order to simulate these things is to have the initial state. And to do that, we use the function init_res_sol, which takes in the grid and then the initial pressure in this case. So let's just make that. Let's look at what it looks like as well. Init has a field pressure. It has a field flux. The flux would be the volumetric flux in between the different cells of the grid. And then it has a field S, which is the saturation, not used here since it's single phase, but generally if you do multi-phase simulations, you'll have something interesting happening with saturations as well. Now we have almost everything we need in order to solve this problem. The final thing is to actually discretize the equations. And we do this here using the 2-point flux approximation method. I'm not going into detail now, but rather just do that later. For now, we're just going to say that we need something called the transmissibility. And for that, we use the function compute trans, takes in the grid and the rock structure. And let's just make that. And then we use the function incomp tpfa, which solves this problem using an incompressible 2-point flux approximation method. And the input to this function is the initial state, the grid structure, the transmissibility that we just created, the fluid object, and the boundary condition struct as an optional input argument. So we're just going to solve this. You can see what the sol looks like. It just as the initial state, it has pressure, flux, and saturation, and it also added this field called phase pressures. And now we're going to just look at what the solution looks like. And this is the pressure in bars. So you can see that it's 100 bars at the top of this model, and then it increases downwards to a little more than 102.5 bars at the bottom of the model. So there we go. We've just put up the first example of MRST, solved that with an incompressible solver with gravity. And I believe this is a good time for a break. I've seen in the chat that there's someone who has a few problems with Octave, and I believe it's related to the GUI stuff. And I'm afraid there's quite a lot of things that are not really supported in terms of the guided user interface functionality. But if you have any questions, of course, ask them in the chat. And I think we'll take a break here of 10 minutes, and then we're going to continue later on. Okay, I think we should start up again and move on to the second part of this tutorial. And now we're going to talk a little bit about the numerical framework of MRST. As I've said before, MRST is really geared towards rapid prototyping, and there's essentially two main things that enables this. The first thing is discrete differentiation operators. So if we consider here a physical, fundamental physical principle, conservation of momentum, given here by Darcy's law, which essentially states that the discharge volumetric flux at a certain point in space equals to minus the permeability in that space times the, in that point, times the gradient of the pressure. And here we've written this in integrated form, so we integrate across an interface gamma f. That would be this interface right here in between two cells, and we multiply, take the dot product with the phase normal of that interface. So that's what you're seeing here, and what we would like to do, of course, is to discretize this. And what we do here is that we use the two-point flux approximation method. And this is essentially based on using geometric information from the grid and the permeability in order to construct transmissibilities that you see here. So we're using the pressure first at the cell centroid, and this is cell I, and at the centroid between, at the interface between the two cells where we're interested in the flux. So then we're using the vector CIK that you see here, connecting the cell centroid to the phase centroid, and we're using the phase normal for this interface together with the permeability in cell I. And then we want the directional derivative, so we had to divide by the length of this vector, and then also once more, because we're interested in the gradient. Details on this you can find in, for instance, the textbook on reservoir simulation with MRST, just showing you the geometric properties and where they sort of enter this expression. And then since we're integrating over the interface, we also multiply by the area of that interface. And that's done from both sides. So one time from cell I to the common interface between cell I and cell K. You do the same thing from cell K to cell I. And then you combine these two transmissibilities into what's the harmonic average, and we get the transmissibility for interface IK. And this is essentially how you construct and derive the two-point flux approximation, saying that the flux between cell I and K equals the pressure difference between these two times this transmissibility IK. The point of this, of course, is to write our expression up here in a discrete form, just like this. So we've gathered here all our fluxes of the interfaces in the entire grid in a vector V. We've gathered all the transmissibilities, and you can see here the gradient of the pressure in a discrete operator. We'll come back to how that's defined in the next slide. So this is how we put up this in discrete form. And F here, this is just for phase number F in our grid. And of course, we need the transmissibility in phase number F, and we're taking the gradient over phase number F. In much the same way, we discretize conservation of mass, which is the other physical principle. Essentially, it states that the net flux out of a volume, omega c, has to be equal to the production of fluids inside that same volume. Using the divergence theorem, we can write this guy here equal to this, and then we can write this in a discrete form, where we have a discrete divergence operator, and we have the sources on the right-hand side. So this is how we discretize the equations. And sort of to get more into details on how we actually do that, we need to talk about how we make our grids. So in MRST and say in reservoir simulation in general, we would like to be able to work with, say, idealized models that you see on the right-hand side here. It could be a simple Cartesian grid or something slightly more complex like this Voronoi type Pebi grid that you see here, and all the way over to full-scale complex industry models. And these can, for instance, be on so-called corner point type format, where you have all sorts of strange topologies. A cell can have a bunch of number of neighbors, not just, for instance, 6 that you would have in a logical Cartesian grid in 3D. I've actually encountered corner point type grids where you have 26 topological neighbors. And we would like something that's able, a grid format, fully unstructured, that's able to deal with everything ranging from simple Cartesian and all the way to these complex corner point type formats, and of course, including Voronoi type diagrams. So the way we do that is that we have a fully unstructured grid format in MRST, which essentially for, say, a cell number 1 here is made up of faces 1, 2, 3, and 4. Then we need a vector so that cell number 1 is made up of these cells. And similar for cell number 2, it's made up of face number 5, 6, 7, 8, and 2, which you can see here. Likewise, we also have information about the topology in that we need to know for a certain face and interface which 2 cells is that interface a part of. So if you, for instance, look at the face here or interface between cell number 1 and 2, we need a vector, or actually a matrix with 2 columns that says that interface number 2 is between cell number 1 and cell number 2. And this also actually encodes the orientation for each of the faces, since cell number 1 is in the first column and cell number 2 is in the second. We say that this face is oriented with a normal pointing from cell number 1 to cell number 2. And this is what enables us to actually write these discrete operators in a very generic way, so that we can write our equations on the same way, regardless of what type of grid we're using, even if we're using a Cartesian grid or if we're over here and doing something very complex. So the discrete gradient operator essentially maps from a cell pair, cell 1 and cell 2, of a face F and onto their common face. So the gradient operator would look like this, say that P is a scalar quantity associated with so one value for each cell, and then the gradient of that value at the face F would be the value at one side of the interface minus the value of the other side of the interface. A very simple discrete gradient operator, which really makes it easy for us to write our equations in a very compact form. And it's very much the same with this divergence operator. The difference is that it maps the other way around, so you have a set of fluxes, one for each interface, and the divergence operator then maps all of these faces down to one value for each cell. Both of these operators are linear, so that we can represent them as sparse matrix multiplications. And the point of all of this is, of course, that we can write our discrete equations in a form very close to what we would do with pen and paper for the continuous equations. For instance, you can look at incompressible flow here with the divergence, and then you have the permeability, and you have a gradient of P plus a source. And in discrete form, we write it in almost the same way. We have the divergence, and then we have this T, the transmissibility that I just described a couple of slides before, times the gradient operator, and plus this Q. And for compressible flow, it's slightly more complex, but it's the same concept. We're using discrete operators for each of these terms to write it in a very compact form, which is very similar to the underlying mathematical expressions. Now, these this is sort of the first building block, this discrete operators. And the second one, we can see the motivation for now. So discretization of flow models, they lead to large systems of nonlinear equations in general. And this can be solved with Newton's method. I'll not go into detail. Essentially, we have a residual equation and we want to solve that, a nonlinear residual equation. We linearize and solve for an update, do that update and continue until we have this guy here is below a certain tolerance. And in order to do this, we see that we need to compute this guy here. That's the Jacobian. And computing this Jacobian and coding that is a very time-consuming and a very error-prone process. So this is where automatic differentiation comes to the rescue. And this is the sort of second main building block that I'm going to talk about today. And the general idea here is that any code consists of a limited set of arithmetic operations and elementary functions. So in automatic differentiation, instead of just working with the value of a function, we introduce an extended pair. So we have the value and its derivative of that function. And then we use the chain rule and elementary derivative rules to mechanically accumulate derivatives at specific values of our variable. So for instance, for elementary operations, such as the sine of x, we are always, when we work with this in AD, automatic differentiation, we use both the value and its derivative, which is the cosine of x. For arithmetics, if you have a product, f times g, you would have the value of f times g and the derivative, which is f times the derivative of g with respect to x, plus the derivative of x, f with respect to x times g. And then you also have the chain rule, and all of this you implement in a convenient way using operator overloading. So the way this would work in practice, you can see a small snippet down here. If you initialize two AD variables, a variable x with a value equal to 1, and a variable y with a value equal to 2, and then you do an expression z, which is equal to 3 times the exponent of the exponential function of minus x times y. So what this would look like is that we then get an ADI variable. This is the class for AD variables in MRST. It's called ADI. So x now has a value 1 and a field jack, which is its Jacobian, its derivatives with respect to all the AD variables. So in this case, we have this is the derivative with x with respect to itself, which is 1, and then the derivative of x with respect to y, which is 0. And then it's the same for y. You get a value 2. You have the derivative of y with respect to x, which is 0, and the derivative of y with respect to itself, which is just 1. And then you have this z here that we made as a composite expression of x and y in the exponential function. So this has a value, and then it has the derivative of z with respect to x, of course evaluated in x equals 1, y equals 2, and the same for the derivative of z with respect to y. So the point of all of this is that instead of actually hard coding derivatives in order to get this Jacobian here, we can get it for free as long as we know how to write down our mathematical expression. Very convenient tool, and this is really what enables us to test different types of fluid physics and also experiment with different types of discretizations and all of these things. So now we're going to actually see this in practice, and what we're going to do is to solve the Poisson equation, both on a structured and an unstructured grid. So this means that we will look at this equation right here, which you would probably recognize from before. We have minus the divergence, and then there's this permeability term. You have the gradient of P, and it's equal to Q. And if we want to write this with discrete operators that we just described, it would look something like this on residual form. So we have divergence, then the transmissibility, gradient of P, and plus Q, and we just call this f of P, and we would like with automatic differentiation to see that we can get this df dp. So let's then go back to MATLAB And we're now going to look at the solve Poisson script. Just a word caution for those of you using Octave. There's two different grids that we're going to use here. The first one is a simple Cartesian one, and then we're going to look at something unstructured. And for that, I'm going to use what's called a C-mount dataset, and I think that's only available in MATLAB, so you will not be able to do that particular part in Octave. But let's just start with this now. We're going to make a Cartesian grid, 3 by 3. We're going to compute the geometry, and let's just look at that and see what it looks like. So this is a simple 2D grid. We're plotting it. Let's just put the axis equal and tight. So here, simple 3 by 3 grid. And we're going to put in sources, so that if we go back to the slide, that's going to be this Q here. We're going to put that into our equation, and I would like to put one source in the center cell. Actually, I would like to put one sink in the center cell, and then I'm going to put the source in this cell and the source in this cell. So we just say that this is, we just put it in here, cell number 5, 1, and 9. And then we just make a rock structure. We need that anyway, but we're not going to actually use any properties here. But since this is a toolbox for subsurface flow, we need to provide a rock structure irregardless. We just give it 1 and 1 in the permeability and porosity fields. So there we have a rock. And what we would like to do now is to set up the operators that I just described. And in order to do that, we need to first load the AD core module. So this module holds all of the main core functionality of the automatic differentiation framework in MRST. I'm just going to add that. And in this module, we will find the function setup operators TPFA, which sets up the operators for the 2-point flux approximation that I described before. And this function takes in the grid and the rock structure. That's because we need the geometrical information from the grid, and we need the petrophysical properties from the rock structure. So let's just call that, and we can see what it looks like. Just minimize this figure a little bit. You see here that this is a struct. It has a T. This is the transmissibilities that we described before. And then you will also find the gradient operator that you see here, and there's a divergence operator. These are both, as I mentioned, linear operators, and they both rely on the topology of the grid. And you see that in these two operator definitions, we can find this matrix C. C here essentially encodes all of the topological information in the grid. So what we're going to do now is to look at the sparsity pattern of this matrix C. So let's do that in the line here. And you can see here that this is what it looks like. It has 12 rows. That's because there are 12 internal interfaces in the grid. And then it has 9 columns, 1 for each of the cells. And essentially what it says here is that interface number 1 is between cell 1 and cell 2, and so on, down to interface number 6. And then you'll see, so those, if we look at the grid, that will be the interface here, 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 here. So all the vertical interfaces. And then starting from row number 7, you'll see that we're in, this is interface, the horizontal interface. So that's going to be this one, and all the way up until we've covered all the interfaces. So we see here that interface number 7 is between cell number 1 and cell number 4. So that's this operator, that's this matrix that enables us to define the gradient and divergence operator. Now let's move on to actually initialize some AD variables and make the equation that we're going to solve. First thing we do is to initialize P here as AD variables. And we do that with the function init variables ADI, and we make it equal to 0. Oops, I forgot to actually store the number of cells in the grid. That's something we need in order to know how many values we're going to use. There we go. And if we now look at P, you'll see that it's an ADI with properties val, which is the values for each of the grid cells. And you'll see that that's simply 0. That's what we initialized it to be. And then you can look at the Jacobian, and let's just actually plot and look at the full Jacobian. It's a sparse matrix, but I'm just writing it to the command window as a full matrix. And you can see here that it's simply the identity matrix. It means that the derivative of P with respect to P is 1, which is exactly what we're expecting. Then we're going to do this, the sources, so that's the right-hand side. And we're just making that equal to 0, and then we're going to put in the sources and sinks at appropriate places. First, we'll put in a source of -1, and then a sink of 0.5 and 0.5 in cells. And I put cells in this case to be cell number 5, 1, and 9. So let's just do that and see that that makes sense. So this is our Q, sources and sinks. And now we have everything we need in order to write down our equation. That's this guy here. Let's just go back to the slide and see that we're in agreement here. We wanted to write this guy here, the divergence, and then we have the transmissibility times the gradient of P, and then plus the Q vector that we just made. So this is what we have here. So let's make that. And again, you see that EQ for equation has a value field and a Jacobian field. And now we're going to look at the sparsity structure of the Jacobian of this equation. So let's just do that. Sparse and enlarge, and this is what we get. And if you've worked with elliptic type problems before and discretized an elliptic operator, you will probably recognize this. This is essentially the typical structure of that. You have this banded structure with these small blocks along the diagonal, which is 3 by 3 because we have a 3 by 3 grid. And then you have these values on the first diagonal and then further on here. So this is what it looks like. And we can now try to actually solve the equation. First, we'll just give a value in one place so that we don't get an ill-conditioned system. So we're just putting in the first element of the equation. We're just setting it to be equal to 0. And then we're going to solve this problem. So this is the Jacobian, and this is the value. And since this is a linear problem, there's no solving necessary in a nonlinear solve. We can just simply solve this expression to get the pressure. So let's just see what that looks like. And this is the solution that we're getting when we're solving for that. We have a low value in where we have a source, a sink, and then we have high values in these two cells where we have sources. And then it's basically almost flat everywhere else, the solution. Not very interesting, so that's why we're going to look at something more complex. We're going to load the C-mount dataset, which is part of MATLAB. So let's just load that first. I'll just close here and close everything, and then we can load the dataset. And you'll see that we now have this X and Y, and we can probably just plot that. So it's essentially a collection of points here, and we're going to use these points in order to make a triangle grid. So that's what we're doing in this line. We have a triangle grid, which I call T, And let's plot that and see what it looks like. So this is the triangle grid made up of those points. And since triangle grids are not really good for this 2-point flex approximation that I talked about for various reasons, which you can, for instance, learn more about in the textbook on MRST, we're going to convert this into a PEBI grid, perpendicular bisector grid, or Voronoi type grid, which some of you may be familiar with. So we're going to do that with the PEBI function, which takes in a grid, a triangle grid T, and let's see what that looks like. So now we have made the triangle grid into this Voronoi type grid, which is a lot better to work with for the TPFA method. And then we're just going to compute geometry and define the cells in which we want to put our sources and sinks. And we're making the rock structure, and again, let's just construct the operators, and we're going to plot them and see what they look like. So this is the sparsity pattern of this matrix C. It looks quite different from what it did for the Cartesian grid, and it's a lot more complex. But it's and this is how it's implemented in MRST, so that we can use the same code regardless of the grid structure. Very convenient in order to implement this discrete divergence and gradient operators. And if we now do the same exercise, we're going to construct the AD variables and make the Q vector with sources and sinks, and then construct the equation. And if we now look at the sparsity pattern of the Jacobian, it looks a lot different than what it did. It's still symmetric, obviously, but it's now much more complex, and it doesn't have this nice banded structure that we saw before, of course, since we're using and dealing with this unstructured grid format. But that's a main point in MRST, that we're not relying on any type of structure of the underlying grid. We have a completely unstructured grid format that allows us to do these discretizations in the same way, regardless of the grid structure. So now we're going to solve, again, as we did before, the same equation, but on a different grid. And this is what we're getting. So we have we put the source in the sink in the middle, and we have a source in each of these two cells here. So you can see that we have this cool elliptic type structure in the solution. So that's essentially what I was planning to talk about regarding this structures, regarding this the numerical framework in MRST. And I think now I'll use the remaining time to go through a more complex example, in which we are going to look at sort of more advanced usage of MRST, and we're going to go through a worked simulation example, where we're going to start by defining a few horizons, and then we're going to extrude this grid in order to mimic stratigraphy. We'll introduce some spectral architecture, add petrophysics, define a bunch of wells, and then we're going to set up a fluid model, an initial state, and we'll simulate this whole thing. And afterwards, we're going to look at some of the nice functionalities for investigating simulation results with the GUI that comes with MRST. So let's just close everything, and we're going to open the workflow demo. For this example, if you're on Octave, there is a separate function called workflow demo _Octave, because there is part of this setup in the beginning that will not run in Octave because we don't have support for a few things. For instance, some interpolation that doesn't behave in the exact same way in MRST and Octave, and also some of the GUI functionalities that we're going to look at will not work properly. The important thing is that the simulator part with the nonlinear and linear solvers, that's going to work. So that's why I've saved the grid that we're going to use here and the rock into a mat file that you can load in Octave so that you can run the same example using this workflow demo underscore Octave. So the first thing we're going to do in this example, as before, is obviously just to load the module. So let's first do MRST module clear so that we have no modules loaded, and then we're going to add what we need. The first thing we're going to add is the AD core module. So this holds, for instance, what we just saw, the setup operators TPFA and some flow models that we're going to inherit from in what we're using. And then we need to load the AD props module. This holds a lot of functionality for setting fluid properties. And then finally, we're going to add the AD black oil module because we're going to use what's known as a black oil formulation of the equations that we're using. Then we're also going to do a lot of plotting in this, and we're going to then use what's in the MRST GUI module, which holds some very useful functionality for plotting and looking at simulation results. So let's just add all of that and list the modules. We see that we have what we said that we'll have, so that's good, and we're ready to begin building our grid. The first thing that we'll do is to build an horizon for the top structure. And we're going to have a 1,000 by 1,000 meter, and we're going to use 40 points in order to define this aerial mesh from which we will construct our top surface. So first we just do that, and then we construct a basic dome structure, which is going to form the foundation of our top surface. So let's just look at what that looks like. So this is the dome structure, and this is what we're going to use in order to build the first surface. So what we would like to add to this is, first of all, some periodic perturbations and some random small-scale perturbations. So what we do then is to first define some normalized coordinates. So we scale them by pi and divide by the maximum dimension so that we have them in between 0 and pi. And then we make the perturbation. It's just, in this case, we're just making a combination of sines and cosines in various ways. So that's the perturbation, which is periodic, and we scale it with a factor 3.5. And if we plot that, you can see that this looks quite interesting. And this is what we're going to add to this dome structure in order to mimic a horizon. And then we're going to add into this some small scale random perturbations. So let's just do that as well. And let's plot the whole thing. Just close what I have first. And let's just plot the whole thing and see what it looks like. So, yes, I see just a question in the chat, and Olav just answered that. If you're an Octave user, I would follow the workflow demo underscore Octave. That's correct. And the point is that you'll have to load the grid that I'm constructing now in the accompanying mat file. Unless you're on MATLAB, then you can just do this construction yourself. But unfortunately, this type of construction is not. You'll probably be able to make this in Octave, but you'll probably not be able to simulate on it because things are generated a little differently. Anyway, this is the top surface. It has this, it's based on this dome structure plus some periodic perturbations plus some random perturbations. And the next thing we're going to do is to add the bottom surface, and then we're going to add a surface in between there. The bottom surface, we just shift 30 meters downwards. So that's this guy here. And in between, we're making a surface based on the bottom surface plus 4 meters. And then we add in some inclination by a plane. And we add in some random small scale perturbations there as well. So we're going to make those. And then we're going to pack them all conveniently into a cell array of structures, which we call horizons. And we'll see in the next cell how this is going to, why we're actually making this into this struct. But just let's construct that. And then we're going to visualize and look at what these look like. So here you can see the horizons from which we're going to build our entire geomodel. Of course, there's many ways to go about making a model in MRST. And this is the reason I'm showing you this is just to show you how you could potentially do it. If you have your horizons stored in some other data format, you're probably able to load them into MRST and construct a grid from that. Or if you have a grid already, you could probably also be able to load that then into MRST and construct a grid. So it's a really, the point is that it should be very flexible, and you should be able to do a lot of different things with the toolbox, depending on what your data looks like. So now we have our surfaces, and we're now going to fill this in with a grid in between. And for that, we have a very convenient tool called Convert Horizons to Grid, which takes in the horizons in this cell format that I just did in the previous section here. And then it takes in a couple of optional input arguments. The first one is dips. That's the dimensions in each of the lateral directions. So in this case, we would like to use a 40 by 40 grid. The second argument is layers. So that's the number of layers of cells that we would like to use in between each horizon. And we would like here to use 6 layers of cells in between the red and the blue horizon. And then in between the blue and the green horizon, we would like to use 3 layers of cells. So this function will give us this function will give us a gridical, which is maybe familiar to some of you, which is a format widely used in reservoir simulation. And then we're using a function called process gridical to process this into an MRST grid. Let's see what the grid looks like now. So just plotting in between these horizons, we're plotting in the skeleton of the computational grid that we're going to use. So now we have a grid. We would like it to be slightly more complex. So we're going to insert a few faults here. And we're doing that by first getting out the corner point nodes of this format, which is a corner point format. So we're extracting the nodes from that, or building the nodes from that. And then we're shifting the Z coordinate at a few places in order to introduce these faults and some structural architecture. And then we use this function again, process. So we're changing the Z-corn field of the gridical struct that we have. And then we use this function again, process gridical, in order to get a grid. So now we have the grid that we're going to use in this simulation. And we are going to compute the geometry, because we need that in order to construct our operators. And then I would like to plot the logical index of, or the layer number, if you like, in the vertical direction. So for that, since this is a logically Cartesian grid, I'm going to use grid logical indices to get the logical index in the vertical direction, and then I'm going to plot that. It looks like a lot of code to plot here. You can really just use plot cell data, but I'm adding in a few things in order to make it look a little nicer. I'm adjusting the view and so on, but you really can do this with just the function plot cell data. Okay, so now this is starting to look like something slightly more realistic. So we can see that we've added in these faults, and we have a bunch of layers. You can see that we've modeled this pinch out in between. We'll put on a little more light in between, so that this horizon that you saw were sort of collapsing into the bottom surface is now modeled as this pinch out, and this is the grid that we're going to use for simulations in this example. So now we have the geological or the computational grid, but in order to actually make this into a model that we can simulate on, we need to populate it with petrophysical properties. And we're also going to do that here. This is the second thing that you will not be able to properly do in Octave, is this log normal, or we're going to generate a log normal permeability field, and this function is not properly supported in Octave. So that's why I also stored the rock that I'm constructing here in a mat file where you can load if you would like to run this in Octave. I'm using log norm layers. It takes in the Cartesian dimensions. It essentially just generates a log normal permeability field in a bunch of layers with a different mean. We're using 100, 400, 10, and 50 millidarcy in 4 different layers here. And this is going to give us a vector k of permeabilities. Since this is now generated on a box with g.cartdims, you can see them here, it's 40 by 40 by 9. But as you see from this model, here we have 9 cells in the vertical direction. But on this side, since this horizon collapsed into the bottom, we only have 6 cells. So we need to extract only the cells that are actually present in this model. And you can do this with this line here. So k of g.cells.indexMap. So this is an index into the grid that would have been if all logically Cartesian cells were there. So now we've extracted the part of the permeability that we would like to use, and we're going to introduce an anisotropic permeability field. It's going to be equal in the x and y directions, but in the z direction, we're going to scale it by a factor of 0.1. So we're just going to construct the permeability there, and then we're going to pass this on to the function makeRock, which you've seen a couple of times now. It takes in g, as I said before, and the permeability. And since we're now in 3D, we're allowed to give this as a diagonal tensor. So permeability in x, y, and z direction. We could also, if we would like that, to give it this as a permeability, a full tensor permeability, and then it would essentially give in the entire upper triangular part of the permeability tensor. And then we just, for simplicity in this case, apply or impose a homogeneous porosity of 0.3 in the entire model. So then we have the rock structure, and this time it has 12,222 rows, this permeability field, and 3 columns, 1 for each of the actual directions. So then we have the geomodel, and let's just visualize that. That's what it looks like when we've added in permeability. And at the bottom here, you can see this is actually the log 10 of the permeability on the color bar. So I'm plotting on the logarithmic axis here. So now that we have the geomodel, the next thing we need to do, or the next thing I would like to do now, is to put in wells to the model. And before I do that, we're going to, so in this case, we're going to add 3 production wells, and they're going to operate at a fixed bottom hole pressure, and we're going to add in 1 injection well with a fixed injection rate. And we would like to simulate, in this case, injection over 10 years. And over the course of those 10 years, we would like to inject a total of 1 pore volume of this entire model. So then we set the injection rate to be equal to the pore volume, the sum of the pore volume divided by the simulation time. So let's just do that, and we'll see that the injection rate is, and this is in SI units, so it's in cubic meters per second. And if we would like to, I could also show you this convert to function. And then we take injection rate and say that you're a petroleum engineer and you would like this to be in standard barrels per day. And it says that the injection rate that we're operating at is about 15,000 standard barrels per day. Convenient function to use if you would like to work with a different unit set than SI units, or if you're used to a different unit set than SI units. Everything in MRST is SI units otherwise. So now we're going to add in the wells in the model, and we're going to use the function vertical well for that. This function takes in a potentially empty well structure. So you're starting from an empty well structure and adding in wells. Second argument is the grid structure, the grid in which you're going to put the well, and then you're giving in the rock. And then the next 3 arguments in this vertical well function is the logical index in X, Y, and Z direction where you want your vertical well to be. So the first one is just the X and the Y. Those 2 have to be scalar. And then the third one, the Z direction, could be a subset of all the vertical layers in the model. Or if you leave it as an empty vector, it's going to essentially perforate all the layers in your model. So that's what we would like here. And then we provide a name to the well. We call it P1 for producer 1. And then there's a field called comp_I, which essentially says what we're going to inject. This is a mandatory field, and it has to match the number of phases that we're working in. We're going to work with a 2-phase model in this case. But if this is going to be a production well, so this field will not be used. But when we're doing injection, of course, this field is very important. We need to know the composition or which phase we're actually injecting into our reservoir. Then we're giving the value, which in this case, we want to be 250 bars. And the type of well, the type of control, we're going to control this with a bottom hole pressure. And then finally, we're also going to define the reference depth. And that's the depth from which we're measuring the bottom hole pressure. And in this case, we just leave this to be 50. So those are the production wells. We're adding that to the model. I forgot to define the offset first. And we're going to add that. And you see that we get the warning here. It's just telling us that the reference depth that we chose for well number P3 is set below the well's topmost reservoir connection. It's okay, but it's nice to know that you're doing this. So that's why this is printing out this warning. Then we're going to add an injector. As I said, we're going to inject at a constant rate, and I defined this injection rate up here. So we're just doing just as before. Difference is that we're giving it a name I1 for injector 1. And then we say that the type of well here is rate. It's controlled by a rate. And let's just add that. Now we've added all the wells. And let's just plot them to see what they look like in the model. So here you can see that we added in production well number 1 in this first sector here, then production well number 2 over here, and then production well number 3 here. And then you can see the injection well is over here. I hope you can see my pointer, even though it's a little tiny on the screen. Okay, so now we have made a geomodel and we've put in wells. And the next thing we need is to make a fluid model. And we're going to work here with a 2-phase fluid model with water and oil. It's going to be immiscible, so it's quite simple in terms of fluid physics. MRST supports a lot more complex physical or fluid physics than that. For instance, there's a module called compositional, which supports a lot of complex compositional simulation capabilities. In this tutorial, we're just, for simplicity, using a simple two-phase water-oil model. So what this function takes in is, first, it's a bunch of optional input arguments. The first one is the phases that we're working with. It's going to be water and it's going to be oil. We just give that as a string. And then we define the viscosity, which we put equal to 1 for the water phase, 1 centipoise for the water phase, and 5 for the oil phase. And you can also see here the convenience with units in MRST. We just write centi times poise, and then we get the units in SI units. So if I write this, you'll see that this is what it gets in SI units. Then we give the density, 1,000 for the water phase and 700 for the oil phase in kilograms per cubic meter. And then finally, we're going to use what's known as Brooks-Corey type relative permeabilities in this case. I'm not going to go into details, but this is probably well known to many of you. And we're going to use exponent 2 for both phases here. Now, this was when I did this, if I do this, this is going to be an incompressible fluid model. But we would like, in this case, to have an oil compressibility unequal to, so we would like the oil phase to be compressible. And the way to do that, or one way to do that, and we do this here, is just to define the compressibility. We'd let it be 0.001 per bar. And then we put the reference pressure equal to 300 bars. And then we're just going to provide what's known as a shrinkage factor in the black oil model. This is essentially how much the volume will shrink from reference conditions down to a certain pressure. So we're just changing that particular function of the fluid object, and let's see what the fluid object looks like now. I'll just clear so it's a little easier to see. And you can see here that the fluid has a bunch of fields. The first one is the surface density of the water. And then there's this B factor, which is something which is typical for black oil models. And it's essentially the shrinkage factor. You can read more about this in the book on MRST and reservoir simulation, if you like. And then we have the viscosity. This is a constant viscosity in this phase. And then there's this relative permeability. And then you can see the same things for the oil phase. The difference with the water phase here is that we now have this B factor, which is going to dictate the compressibility of the oil phase, which is equal to this exponential function that we just defined. So that's the fluid model. And now we would like to put this all together. We have the computational grid, we have the rock structure, we have a fluid. So we'd like to put this all together in a simulator class. So first thing we do before we do that is to do gravity reset on. Just as I showed you before, let's just validate that this is still what we expect it to be. You can see here that it's equal to the acceleration of gravity in the positive Z direction. So we're still on Earth. That's good. Now we're going to construct a model, and we're going to use what's known as the generic black oil model for that. This takes in the grid structure G, the rock and the fluid, and then we say that we're not having a gas phase, so we have to set the gas property of this model to false. So let's just construct that. And since this is a little interesting, we'll look at the fluid model. I just forgot one thing there. So let's just plot the fluid model here. Okay, so now inspect fluid model is a function that you can use in order to inspect the fluid model that is on a simulator model or simulator class. And here I've chosen the density. You can see how this varies with the pressure. The blue is water and the red is oil. So the blue density of water is constant and equal to 1,000 kilograms per cubic meter, whereas the density of the oil phase increases from about 500 kilograms per cubic meters at almost 0 bars, and all the way up to almost 950 kilograms per cubic meters at 600 bars. So we added some compressibility. You can also, if you like, look at the relative permeabilities. This is the quadratic relative permeability of Brooks-Corey type. And these are equal for water and oil, so they're plotted exactly on top of each other. That's why you just see the red curve. So then we have the fluid model. Now we're almost ready to start simulating. What we need, of course, is an initial state. And in this case, we're going to construct an initial state where we have a water-oil contact at 85 meters depth. And then we're going to use a datum depth from which we'll compute the pressure at 10 meters. And to initialize this in a hydrostatic equilibrium, we use something called init state black oil. So we're just going to do that, and then we have an initial state. You can see state 0 here, and it has a pressure field and a saturation field. So let's just plot that and see what it looks like. I've actually plotted now the saturation of the initial state. Where it's green, it's only oil, and where it's blue, it's only water. And I've also plotted this water table as a patch, so you can see this blue square, which slices through the entire model. So we have, if we rotate it a little bit and put them a little more light, you can see that you have some regions which are completely filled with water, and you can see where the water table is. So that's going to be our initial state. And we're almost ready to start simulating. The only thing left now is essentially to define the simulation schedule. We would like, in this case, to use approximately 25 time steps. That's going to give us a time step size of approximately, I think, 140 days. And then we would like to take a little shorter time steps in the beginning. So we're doing this by using this function ramp up time steps, which takes in a target simulation time and then a target time step size. And then it's going to gradually ramp up the time step from something small to this 140 days. So let's just plot them and see what they look like. So time steps is just a vector. So you can just plot them. Let's also plot them as days. So this is what the time step looks like. They start off quite small, about 4 days time steps, and they're then increasing up to this target time step size of 140 days. And then you get this very small time step at the end. That's just to actually match the target simulation time, which is 10 years. And we can also, of course, verify that the time steps sum up to, and if we divide by year, we see that they sum up to 10 years. So this is what we're aiming for. Simulation of 10 years with time steps starting out quite small and then increasing up to 140 days. Then we just define a schedule, and we use the function simple schedule, where we give in the time steps, and the optional input argument would be the wells, because that's the control that's going to be used at each time step. So let's just do that, and we can see what the schedule object looks like. So this is now a struct with a field step, and schedule.step holds the value, so that's the size of the time steps. It's 32 of them. And then there's something called control, which tells us which control we're going to use at each time step. And after the schedule.control, we're going to see that this is a single control, which has the well structure that we just defined. And essentially this says that this is the control we're going to use at all time steps. And finally, we're just going to pick a solver. You can do this in a number of ways in MRST, just as with many other things. But we need a nonlinear solver, and it needs to have a suitable linear solver, because the system we're going to solve now is rather large. It's not a super large model. It just have about 12,000 cells, but it's nice to have a compiled iterative linear solver. And with this function called get nonlinear solver, it's going to look at the model and pick what it thinks is a suitable solver for this setup. So now we're almost ready to start simulating. We're going to do something which is simulation monitoring. So we'll set up something that plots stuff for us while we simulate, so that we can monitor the simulation and see how it progresses. And we do this using this get plot after step function that you can see here. There's examples in MRST on how to actually do that, but what it does is that it puts up some figures, and I'll explain them while we simulate. Because in the next cell here, you can see that I'm calling this simulate schedule AD function, and this takes in the initial state, the model, and the schedule, and then it has some optional input arguments. The first one is a non-linear solver, so we give in the solver object that we just got, and this after step function, which is going to plot something for us after each time step, so that we can see what and how this simulation proceeds. And then it spits out this well solutions, the states, and the reports, which we'll look at when the simulation is done. So let's just start this and see what happens. You'll notice that this function prints out some information to the command window. It says which time step we're solving. It says how long it is. And then if you look at the figures that we got up, you can see that it's a little crammed because of that I've docked this figure window. But you can see here that we have this simulation panel. This is the number of nonlinear iterations that we're spending for each of the time steps. So that's this plot that you see here. And then you have some progress bars saying how much of the entire simulation schedule that we've done, and also how much of the total simulation time that we have finished with. And then there's this plot here, which shows the dynamics changing in the grid. What you're seeing now is the water saturation and how this changes, and the injected water propagates through the reservoir and reaches the producer number 1, 2, and 3 at different times. So now the simulation is actually done. So that's how quick that was, at least on my computer. Another thing which I also brought up during this simulation is this well solutions. And what you can see here is, and what I'm plotting here, is the water production rate at surface conditions in producer 1, 2, and 3. So you'll see the blue one is for producer 1, the red is for producer 2, and the yellow is for producer 3. So you can see that most of them starts out with 0 water production rate, and then it increases as the injected water reaches the producer at slightly different times. I see here a comment in the chat, by the way, that MATLAB is significantly faster than in Octave, and that's most likely correct. I think it's going to be a little more efficient. There should be compiled. So if you ran this script, it should have compiled and set up the linear solvers, iterative linear solvers in Octave as well. But if it didn't, then it's going to take a lot more time, because then it's just using the regular backslash or ML divide operator of MATLAB or Octave, which is really not efficient for problems of this size. But it should be possible to use the compiled iterative linear solvers also in Octave. So that was the plot well solutions, and you can do a bunch of stuff here. I think let's just look at the injector. So for instance, if we plot the producer bottom hole pressure, you can see that they're all equal to 250 bars. This is what we prescribed. But for the injector, we prescribed a constant injection rate. So instead here, what's varying is the bottom hole pressure. And then you can also do some other useful stuff. You could, for instance, change the unit system. So if you would like to have this, let's say we're interested in the sorry, let's say we're interested in the oil production rate. Let's take the oil production rate at surface conditions in SI units, so we get this in cubic meters per second. So this is what it looks like, and we can also change the label on the x-axis here, or we can change the scale on the x-axis. So let's change to, yeah, that's not possible now. I'll just close everything, and what we're going to do now is to plot the well solutions. That's just what we had up, but I'm now going to also provide the time step sizes. So let's do that, because if we do that, then you will also be able to, then you can see some scales, then you can actually see the scale on the x-axis. And if we now plot the oil production rate at surface conditions, and we would like to change to years, you can see that we, instead of seeing days, we're now going from 1 year to 10 years on the x-axis. And then we can change to, for instance, fields, which would be in standard barrels per day field units. So there's a bunch of useful features you can use here. Let's also bring up the plot toolbar function. So this is another function. I think this is one of my favorites. I'm going to now plot toolbar and call this with the grid G and the states that I just got from the simulation. And I'll just undock this figure to really take advantage of, I hope you can still see my screen. If not, please tell me in the chat. But this is a very useful feature for dynamically plotting and sort of interactively investigating simulation results. So now I'm plotting the pressure, and you can play forward in this simulation and stop at different time steps. So now, for instance, I would like to look at the pressure at time step 27, and we can see that this is what it looks like. I can switch to the saturation, for instance, and rotate, look at what things and where we have a water saturation. And you can also go in and put on limits on the displayed data. So say I would like to look at the water saturation from 0.2. I would only like to plot cells where the water saturation is greater than 0.2. And then you can see that we are not plotting all of the cells, just where the water saturation is above this threshold. You can put on the grid. So lots of useful stuff that you can do and really investigate and understand the results that you just simulated. I just saw a question in the chat regarding setting up the linear solver, and I can maybe repeat that. So where we set up the linear solver was in this line 168 here. This actually happens inside the function get nonlinear solver. And in here, it's going to choose a linear solver. So it's calling the function select linear solver AD. Based on the model that we have, it's going to pick what it thinks is the best option for that. And I think, I'm afraid I don't have time to go into more details on that, but I just saw one more question an error. For those of you who are on Octave, I don't think you will be able to use this plot toolbar functionality, I'm afraid. At least not yet. I hope that we'll have something working for that pretty soon, but for now, these things are simply not supported in Octave. I see that there's 2 minutes left before this has gone on for 2 hours, and I think I'll end things there. I will stay around in the chat and keep an eye on that for the next. I'll keep an eye on the chat throughout the week, I think, and I'll try to answer as good as possible. I'll also at least keep a close eye on the chat for the next hour or so. I would like to thank you all very much for listening in, and I would also like to thank all my colleagues for helping me answering the questions. I've seen that Olav Møyner has been very active in the chat, and that's very nice to have good help there. So thank you very much, everyone, and I really hope that you got something useful out of this tutorial.
Fantastic. Thank you, Øystein. That was really a great tutorial. It was interesting for me. Reservoir simulation is nothing it's not my field at all, so it was very interesting to me. But also I got me the chance after 15 years or so to try Octave once again, and it's come a long way. I was quite impressed with Octave. We continually increased the viewers during your whole 2 hours show, so there were more and more watching, and I'm sure there will be watching many more during the coming months and years. So please hit like and subscribe to Software Underground if you liked what you saw. I would also like to thank you, Øystein, and all your helpers in the channels answering questions. Again, I would like to thank Studio X for sponsoring Software Underground, the Transform 2021 conference, and I hope to see you all around for other tutorials. Thanks, everyone. Bye-bye.